A galaxy drifts alone in the immense, silent black. What if our home is not permanent, but a waypoint in a journey lasting billions of years? This is the grandest story the universe might be telling, the story of the Great Cosmic Migration. It is the epic idea that everything, from the largest galaxy to the smallest seed of life, is on the move across the cosmos. By the end, you will see the night sky not as a static painting, but as a map of the greatest voyage of all. We will uncover why galaxies are pulled toward unseen monsters and how life could be a stowaway on dark, wandering worlds. What does it mean for our own future if the very stars are restless? Our home galaxy is sailing through the void at over 600,000 miles per hour. This is not a random drift. The Milky Way, our nearest galactic neighbors like Andromeda, and dozens of smaller galaxies are all bound together in a cluster astronomers call the local group. But this entire family is not sitting still either. Picture a leaf caught in a gentle river current. That is our local group falling gracefully, irresistibly, toward an immense gathering of matter known as the Virgo supercluster. This is the first layer of the cosmic migration. We are part of a flow, a vast river of galaxies moving through the darkness. Scientists map these movements by observing thousands of galaxies, tracking their subtle red and blue shifts in light, and they see patterns. They see streams and filaments, great walls and enormous voids. The universe, on its largest scale, looks less like a random scattering of stars and more like a colossal, three-dimensional spiderweb. Galaxies line the strands of this web, and the empty spaces between the strands are cosmic deserts, millions of light years across with almost nothing in them. This is the large-scale structure of the cosmos, and everything within it is flowing along these invisible threads. The motion is undeniable, but it prompts a deeper, more thrilling question. Are these galaxies simply drifting like leaves on a river, pushed mindlessly by gravity? Or is there something more? Could these vast flows be cosmic highways, routes etched into the fabric of space-time that galaxies naturally follow over billions of years? The idea transforms our view from one of passive drifting to one of purposeful journeying. It suggests that the migration of galaxies might not be a chaotic accident, but a fundamental process of the universe, as natural as the orbit of a planet. If that is true, then where is this great river of stars ultimately taking us? This cosmic river we are riding has a definite destination. In about 4 to 5 billion years, our Milky Way will complete a migration that has already begun, merging with our colossal neighbor, the Andromeda galaxy. This is not a story of a catastrophic crash, but of a slow, graceful, and inevitable dance. Right now, Andromeda is hurtling toward us at a breathtaking 250,000 miles per hour. Yet the distances are so incomprehensibly vast that this approach will take billions of years to unfold. When the two galaxies finally meet, it will be a gentle intertwining, not a violent collision. Think of two vast crowds of people slowly passing through each other in an open field. The individuals, the stars, are so far apart that they will rarely, if ever, actually strike one another. Instead, the immense gravitational forces of the two galaxies will pull and stretch them, drawing out great tidal tails of stars and gas, weaving their structures together over eons. The stars themselves will migrate, flung onto new orbits, some cast out into the intergalactic void, while others are drawn toward a new, bustling center. After this long celestial dance, the two spiral galaxies will coalesce into a single, enormous blob of stars, an elliptical galaxy that astronomers have playfully nicknamed Andromeda. This merger is a local migration event of staggering scale. Every star in our night sky, including our own sun, will be given a new address in this reshuffled cosmic metropolis. Our solar system will likely be flung much farther from the galactic core into a quieter suburban region of this new giant galaxy. It is a preview, a small-scale model of the kinds of galactic interactions and migrations that are commonplace across the universe. If galaxies can merge and reshape themselves so completely, what other, grander journeys might they be undertaking? The collision with Andromeda is just one step in a much longer voyage, pulling us towards something even more immense and mysterious. The merging of Andromeda will scatter countless stars into new orbits, but some objects face a far more solitary fate. While galaxies migrate in great herds, individual worlds can be cast out entirely, becoming permanent exiles in the dark. These are the rogue planets, and they represent the most profound and lonely form of cosmic migration. A rogue planet is a world that has been violently ejected from its home star system. Picture a young, chaotic solar system with giant planets like Jupiter jostling for position in a gravitational dance. Sometimes, during these close encounters, a smaller world can be slingshotted with such force that it breaks free from its star's gravity entirely. It is flung out into the interstellar void, a dark orphan set adrift between the stars. These are not rare accidents. Current estimates suggest there could be billions, even trillions, of these nomads in our galaxy alone, potentially outnumbering the stars themselves. They wander in perpetual night, their surfaces frozen to temperatures near absolute zero, with no sunrise ever to warm them. Their migration is one of absolute isolation. Yet this leads to a staggering possibility. What if life, against all odds, found a way to cling to such a world? We often think of life as requiring a star's warmth, but consider the oceans hidden beneath the icy crust of moons like Europa or Enceladus in our own solar system. They are warmed not by sunlight, but by the internal heat generated by gravitational squeezing and radioactive decay. A large rogue planet with a thick insulating layer of ice over a subsurface ocean could theoretically maintain liquid water for billions of years as it drifts through the galaxy. If life began on such a world before it was ejected, or even somehow arose in the darkness, it could persist. This means life itself could become a migrant, traveling independently of any star. A rogue planet carrying a subsurface biosphere would be a self-contained ark, sailing the galactic currents for eons, completely undetectable to our telescopes in the profound blackness. It is a haunting thought. The greatest migration of life in the universe may not be happening on sunlit worlds, but in the lightless, frozen depths of these eternal wanderers, carrying biological whispers from one star system to another without ever seeing a sun. If life can travel this way, then our entire concept of a habitable zone shatters, expanding to include the infinite highways of dark space between the stars. While rogue planets wander in frozen silence, other migrants blaze across the cosmos in a trail of brilliant light. These are the stellar runaways, stars kicked from their galactic homes with such incredible speed that they are destined for the eternal void. The most extreme of these are hypervelocity stars, and their story begins in the most violent place imaginable, the heart of our own Milky Way. There, lurking in the darkness, sits Sagittarius, a star, the supermassive black hole that anchors our galaxy. Its gravitational grip is unimaginable, but it can also act as a cosmic catapult. Picture a binary star system, two stars orbiting each other, drifting too close to this monstrous gravity well. The black hole's immense pull can tear the pair apart, capturing one star into a tight orbit and violently flinging the other outward at a staggering fraction of the speed of light. This is not a gentle nudge, but a gravitational slingshot of astronomical proportions. One such star, known as S5HVS1, was discovered racing away from the galactic center at over 3.5 million miles per hour. At that speed, it is not just leaving its neighborhood, it is achieving escape velocity from the entire Milky Way. This star is a true pioneer, a solo migrant on a one-way journey into the intergalactic wilderness. Its trajectory is a lonely line drawn from the bustling galactic core out into the profound emptiness between galaxies. It will sail through the dark for billions of years, its light growing steadily dimmer to any observer left behind until it is alone in a sea of nothingness. But not all stellar runaways come from black hole interactions. Some are ejected from dense star clusters through complex gravitational billiards, where close encounters between multiple stars can boot one out with tremendous force. These high-velocity stars represent a different kind of migration. They are not drifting with a galactic current, nor are they dark, frozen worlds. They are brilliant, active, and utterly alone, carrying their own heat and light into the cold frontier. They become lighthouses with no ocean, beacons traveling through deserts where no one will ever see their light. If galaxies are herds migrating across the cosmic landscape, then these hypervelocity stars are the scouts, the lone explorers shot far ahead of the main group. They are testing the void, mapping the emptiness that the galaxy itself may one day traverse. Their existence proves that the cosmos is not a static museum, but an active and sometimes violent engine, capable of hurling its very building blocks across unimaginable distances. And if stars can be thrown clear of their homes, what else might be traveling these lonely paths, carrying the potential for something even more unexpected? These stellar runaways are the exception, not the rule. For most stars, migration happens within the great herd, a process governed by a far more brutal cosmic law. Galaxies do not just drift and merge, they consume one another. This is galactic cannibalism, a forced and violent form of migration that has shaped our own Milky Way from its very beginning. The largest galaxies in any region grow not just by collecting gas, but by devouring their smaller neighbors. Picture a vast spiral galaxy like our own, its graceful arms spinning in the dark. Now imagine a much smaller dwarf galaxy drawn inexorably into its immense gravitational well. As it approaches, the smaller galaxy is stretched and torn apart by tidal forces, its stars stripped away and pulled into long, shimmering rivers that slowly wrap around the predator. This is not a quick collision, but a slow-motion feast lasting billions of years. The consumed galaxy loses its identity entirely, its stars becoming permanent migrants absorbed into the larger system. And we have the evidence for this written across our own night sky. Astronomers mapping the outer halo of the Milky Way, the sparse cloud of ancient stars that surrounds our bright disk, have discovered something astonishing. They have found stellar streams, faint ribbons of stars arcing across the darkness. These are the galactic fossils, the dissolving skeletons of dwarf galaxies our Milky Way has consumed over the eons. One of the most famous is the Sagittarius dwarf spheroidal galaxy, caught in a death spiral around the Milky Way. With each pass, it leaves behind a trail of its stars, a glittering scar in the halo that marks its ongoing assimilation. Every star in those streams is a migrant, violently relocated from its original home galaxy to a new one. This process frames migration in a stark new light. It is not always a journey of choice or a gentle drift. For countless stars, it is a catastrophic upheaval, a forced relocation enacted by the ruthless mechanics of gravity. Yet, from this destruction comes new structure. The cannibal galaxy grows larger and more massive, its halo enriched with these captured stars. The migrant stars themselves, while ripped from their siblings, find a new place in a grander scheme. They become part of the larger galaxy's history, their chemical signatures telling astronomers the story of the merger long after the event. This means our own galaxy is a melting pot, a cosmic empire built from the assimilation of countless smaller kingdoms. Our sun might well be an original citizen of the Milky Way, or it could be a descendant of stars that migrated here from a devoured dwarf galaxy billions of years ago. We are likely all the products of this ancient hierarchical migration. The largest structures in the universe grow by consuming the smaller, in a cycle of creation through destruction that has been running since the first galaxies formed. And if galaxies are shaped by such violent mergers, What invisible force could possibly be guiding the migration of entire clusters of galaxies on the largest scales of all? This immense river of galaxies, the Virgo supercluster we are part of, is itself in motion. We are not floating aimlessly. Every map of cosmic velocities reveals a startling truth. Our entire galactic neighborhood, along with thousands of other galaxies, is being pulled toward a specific point in the distant cosmos. Astronomers call this mysterious focal point the Great Attractor. It is a gravitational anomaly of staggering power, located roughly 250 million light-years away in the direction of the constellation Norma, the Carpenter's Square. This is not a single bright object we can easily see. Think of it as a colossal weight, a deep well in the fabric of space-time, bending the paths of everything around it. Our local group, the Virgo supercluster, and even larger structures are all streaming toward this unseen epicenter. It appears to be the grand destination for a regional migration of matter on a scale that defies human comprehension. For decades, this posed a profound observational challenge. The direction of the Great Attractor lies directly behind the crowded, dusty plain of our own Milky Way. This region is known as the zone of avoidance, where the thick clouds of stars, gas, and dust in our galaxy's disk blot out our view of the distant universe beyond. It was like trying to see a distant mountain range through a dense, permanent fog. The Great Attractor was a shadow, inferred only by its immense gravitational pull on everything around us. What could possibly possess enough mass to tug on thousands of galaxies? The mystery deepened, suggesting our understanding of cosmic structures was incomplete. If the Great Attractor was the destination, what lay at the end of this unimaginable journey? The Great Attractor was a profound mystery, but it was only the beginning. Astronomers peered deeper, mapping the motions of not just galaxies, but entire clusters of galaxies. What they found was not a simple drift toward a single point, but something far more unsettling. There appeared to be a vast, coherent current, a streaming of matter on the largest scales they could measure. This phenomenon earned a name that sounds like it belongs in a cosmic thriller, dark flow. It is one of the most controversial and mind-bending ideas in modern cosmology. To understand it, we need to look at the oldest light in the universe, the cosmic microwave background. This is the faint afterglow of the Big Bang, a snapshot of the infant cosmos when it was just 380,000 years old. This light fills the entire sky with near-perfect uniformity, a relic radiation that is the same in every direction with only the tiniest of ripples. But when scientists studied this ancient light with extreme precision, they noticed a strange and persistent anomaly. The hot and cold spots in this cosmic background appeared to be subtly shifted, as if the entire fabric of space in one hemisphere of the sky was being tugged in a specific direction. This shift, this dipole, is partly explained by our own motion through space. We are moving relative to this background. But when you subtract all the known motions, the pull of the local group, the Virgo supercluster, and even the Great Attractor, a residual signal remains. Something seems to be pulling on galaxy clusters at the very edge of our observable universe, causing them to stream in a coherent direction that cannot be explained by any visible structure within our cosmic horizon. The implication is staggering. It suggests the gravitational influence of something truly colossal that lies beyond what we can see. Our entire observable universe, a sphere nearly 100 billion light-years across containing everything we will ever know, might itself be in motion. It might be migrating, pulled by the gravity of something unimaginably vast that resides in the unobservable cosmos beyond. Picture standing on a raft in the middle of a vast fog-shrouded ocean. You can only see a few miles in any direction, the limit of your observable world, but you feel a strong, steady current pulling your raft in one direction. You look around your visible horizon and see no land, no source for the current. You are forced to conclude that beyond the fog, outside the realm you can perceive, lies something immense, a continent or a whirlpool whose influence reaches you across the void. That is the essence of dark flow. It hints that the structures we see, the superclusters and voids, might be just local geography within a much grander landscape we cannot see. If true, then the Great Cosmic Migration is not just the story of galaxies drifting within our universe. It is the story of our entire universe as one complete entity, being drawn toward an unseen neighbor in a multiverse we can only infer. It raises a profound question. Could this external pull be the ultimate driver, the prime mover, setting entire universes in motion along pathways we cannot begin to map? The Great Attractor is powerful, but it is not the ultimate destination. It is itself being pulled. To understand the full scope of our journey, we must look even farther, to a structure that makes the Great Attractor seem almost modest by comparison. This is the Shapley supercluster, the single greatest concentration of galaxies we have ever observed. Located over 650 million light-years away, it is a staggering metropolis of matter. While the Great Attractor is a dense knot in the cosmic web, the Shapley supercluster is the entire central hub of a continent. It contains tens of thousands of galaxies packed into a region of space so massive its gravity dominates our entire corner of the universe. Think of the Great Attractor as a large city that draws in traffic from its surrounding towns. The Shapley supercluster, then, is the megalopolis that draws in traffic from entire regions, including that large city. Our Virgo supercluster, with the Great Attractor at its heart, is not moving toward the Great Attractor alone. We are all together flowing toward Shapley. This reveals a clear hierarchy in the cosmos, a nested set of gravitational influences. Stars migrate within galaxies. Galaxies migrate within clusters. Clusters migrate within superclusters, and superclusters like ours migrate toward the most massive nodes in the universal web. The Shapley Attractor is the biggest pull we can actually see. Its immense gravity is the primary force sculpting the motion of our local universe, bending the paths of galaxies across hundreds of millions of light-years. To visualize this, picture the cosmic web not as a flat spider's silk, but as a vast, three-dimensional watershed. The galaxies are like water droplets on a mountainous landscape. They trickle down small gullies toward streams. The streams merge into rivers, and all those rivers ultimately flow toward the deepest, largest valleys, the superclusters like Shapley. We are in one of those rivers. Our entire galactic neighborhood is following this gravitational slope, descending into a valley of darkness and light so immense it defies human scale. This migration is slow beyond comprehension, taking tens of billions of years, but the direction is set. We are part of a flow that was determined by the distribution of matter when the universe was in its infancy. So the next time you look up at the seemingly static night sky, remember you are looking at a snapshot of a journey. Every star, every galaxy is in motion, caught in a gentle but inexorant drift toward a distant, luminous continent we call Shapley. It is the largest known landmark on our cosmic map, the place where, for now, the great river of our migration appears to be headed. But the migration of matter, of stars and galaxies, is only half the story. What if the most precious cargo in the universe is not rock or light, but life itself? This leads us to a profound and ancient idea called panspermia. It is the theory that the seeds of life, or life's fundamental building blocks, are not unique to any one world. Instead, they are migrants capable of traveling from one planet to another, hitching rides on celestial vagabonds like asteroids and comets. In this view, life is not a local phenomenon that sparks into existence in isolation. It is a cosmic traveler, and planets are merely temporary ports where it finds shelter, grows, and perhaps one day departs again. This transforms our understanding of biology's place in the universe. If true, life on Earth may not be native, we could all be descendants of interstellar pioneers that arrived billions of years ago, carried here on a rock from another star system. The mechanisms for this are startlingly plausible. When a large asteroid or comet strikes a planet with microbial life, the impact can blast fragments of that world's crust into space. Some of those fragments, containing hardy microorganisms nestled deep within the rock, could be ejected with enough force to escape their planet's gravity. They become tiny, dark arcs sailing the solar system. If another fragment eventually crashes into a suitable new world like a young, wet Earth, those microbial stowaways could awaken in a new home. We have evidence that makes this more than just speculation. Scientists have found amino acids, the organic building blocks of proteins, on certain types of meteorites. These are not contaminants from Earth, but complex molecules formed in the ancient solar system. It proves that the raw ingredients for life can be manufactured in space and delivered by natural processes. Even more compelling is the incredible resilience of life we already know. Consider the tardigrade, a microscopic animal often called the water bear. These near-indestructible creatures can survive conditions that would instantly kill almost anything else. Researchers have exposed tardigrades to the vacuum of space, brutal radiation, and temperatures near absolute zero, and they have revived after returning to a hospitable environment. If a complex, multicellular animal from Earth can endure such a journey, it is not a leap to think that simpler, hardier bacteria could survive an interstellar trip nestled inside a protective shell of rock. This paints a breathtaking picture of cosmic ecology. A single impact event on a life-bearing world could scatter millions of biological capsules into the galactic void. Some might fall onto barren worlds, perishing. Others might land on worlds with liquid water and the right chemistry, seeding them with life. In this scenario, life migrates opportunistically, using natural astrophysical processes as its transportation network. It means a galaxy could become biologically connected, not through radio signals, but through the slow, relentless exchange of material between star systems. Our own solar system may have traded rocks with its neighbors in the distant past. Martian meteorites found on Earth prove that material moves between planets within a single system. Scale that up over billions of years, and the entire Milky Way could be engaged in a slow, silent conversation, exchanging not just minerals and water, but the very spark of life itself. This suggests that we may be living in a galaxy that is not just migrating, but is fertile, where life spreads like pollen on the stellar wind. Panspermia presents life as a cosmic stowaway, a fortunate accident catching rides on wandering rocks. But what if some of those journeys were no accident at all? This leads to one of the most provocative ideas in all of science, the concept of directed panspermia. It is the theory that an ancient, intelligent civilization, perhaps facing its own extinction, deliberately seeded the galaxy with the building blocks of life. They would not have sent spaceships with astronauts. Instead, they might have launched sterile, robotic probes, their cargo holds filled with durable, freeze-dried microorganisms aimed at promising young star systems. The goal would not be to send themselves, but to send their legacy, ensuring that the flame of biology, once lit, would continue to burn somewhere in the dark. This is not science fiction fantasy, but a hypothesis seriously considered by some of the brightest scientific minds. The Nobel Prize-winning co-discoverer of the structure of DNA, Francis Crick, alongside chemist Leslie Orgel, published a paper on this very idea. They pondered whether life on Earth might be the result of such a deliberate seeding event. Their motivation was not to prove it happened, but to ask a legitimate scientific question: could the evidence allow for such a possibility? The logic is hauntingly compelling. Imagine a civilization that has reached a technological peak, only to foresee an inevitable catastrophe, whether a dying star, a galactic cataclysm, or their own self-destruction. Their planet, their entire history, is doomed, but they possess the knowledge to encode their biological essence into resilient microbes. By launching thousands of small, targeted probes toward distant, habitable-looking worlds, they could achieve a form of immortality. Their genetic legacy, in some adapted form, would live on billions of years later on a planet like Earth. The motivation might not just be survival, but a form of cosmic gardening or terraforming on a galactic timescale. By introducing hardy, photosynthetic bacteria to a planet with water and an atmosphere, they could slowly, over eons, engineer that world's environment, making it more suitable for complex life to eventually arise. It is the ultimate long-term project where the gardeners are long gone, but their carefully selected seeds are still growing. This idea flips our entire perspective on biological migration. It suggests that the spread of life might not be a random, blind process, but a carefully orchestrated one. It introduces the specter of intelligent design, not from a supernatural source, but from a prior, natural civilization that arose elsewhere in the cosmos. The profound question it raises about our own origins is unsettling. If directed panspermia were true, then every living thing on Earth, including us, would be part of a grand, ancient experiment. Our DNA, the very code of life, might contain not just the history of evolution on this planet, but a faint, encrypted signature of its original senders. Are we the intended outcome, or merely a wild, unexpected branch on a family tree planted by strangers? This transforms the great cosmic migration from a story of physics and chance into a potential story of purpose and legacy, written in the language of biology across the stars. All these possibilities of migrating life lead us to a haunting silence. If the cosmos is so vast and ancient, and life has had every chance to spread, why do we see no signs of it? This is the essence of the Fermi paradox, the famous question posed by physicist Enrico Fermi: where is everybody? The universe should be teeming with advanced civilizations, their radio signals and megastructures evident across the galaxy. Yet we hear nothing but cosmic static. Perhaps we have been looking for the answer in the wrong place. Maybe the silence is not a sign of absence, but a clue about movement. One compelling solution to this great paradox is that advanced civilizations do not stay put. They migrate. When a species masters its home world and then its solar system, its ultimate destiny may not be to broadcast from a single point, but to leave it behind entirely. Think of it like this: humanity, as a young technological species, is still nest-bound. We are focused on our cradle, Earth, but a civilization 1,000 or 1,000,000 years more advanced would likely view its home star as a temporary resource, a launching pad. Their goal would be to disperse, to ensure their survival by not having all their eggs in one stellar basket. This migration could take two profound forms. The first is physical expansion. A civilization might build vast, self-sustaining arcs, generational ships that travel for millennia, hopping from star to star, harvesting resources and moving on. They would become galactic nomads, always in transit, their presence so fleeting at any one star that we would be unlikely to catch them. The second form is even more alien. A civilization might transcend biology altogether, uploading its consciousness into durable, efficient machines or into the very fabric of space-time itself. This post-biological intelligence would have no need for planets, atmospheres, or even stars as we understand them. It might migrate into optimal regions of the universe we cannot perceive, like the calm neighborhoods near supermassive black holes where immense energy is available, or into the diffuse clouds of the intergalactic medium. They would operate on timescales and in dimensions that make them invisible to our brief biological senses. This idea turns the Fermi paradox on its head. The reason we do not see great empires centered on stars is because those are the relics, the abandoned birthplaces. The truly advanced have moved on. They might be all around us, but in forms or places we simply do not recognize. Their vast computational networks could be hidden in plain sight, using the quiet cold of deep space as their substrate, their communications happening through quantum channels we cannot yet access. The cosmic silence, then, is not empty. It is the quiet hum of a universe where intelligence has become like water. flowing to where the conditions are best, leaving behind dry riverbeds of dead worlds for newcomers like us to find. We are not alone in a crowded galaxy. We are late to a party that has already moved to a better location. The galactic suburbs may hold the key to a civilization's longevity. Far from the brilliant, crowded disk of a galaxy like our Milky Way lies a vast spherical cloud known as the galactic halo. This is the final frontier of a galaxy's territory, a region of profound darkness and unimaginable scale. Here, stars are few and far between, lonely sentinels adrift in an ocean of emptiness. But this emptiness is an illusion, for the halo is dominated by something we cannot see, dark matter. This mysterious substance, which makes up most of a galaxy's mass, forms an immense, invisible gravitational scaffold holding the entire structure together. For a civilization thinking in terms of billions of years, this sparse, quiet realm offers irresistible advantages. The chaotic core of a galaxy is a dangerous place with frequent supernova, intense radiation, and the gravitational turmoil of orbiting black holes. The halo, by contrast, is a place of profound stability. A habitat placed here would face few cosmic threats, a quiet backwater in the stellar metropolis. But the real resource might be the dark matter itself. While we do not yet understand how to harness it, a Type 3 civilization on the Kardashev scale, one that commands the energy of an entire galaxy, might see the halo not as empty but as rich. Dark matter could be the ultimate energy source, a fuel tank for cosmic engineering on a staggering scale. This is where the classic idea of a Dyson sphere transforms. We often picture it as a shell built around a single star, but in the halo, a civilization might construct not one sphere, but millions of them, each capturing the total output of a star and distributing these energy-harvesting platforms across the vast volume. They would create a diffuse, galaxy-wide network, a glittering web of habitats and power stations suspended in the dark. These halo megastructures would be invisible to us at interstellar distances, their waste heat lost in the cosmic background. For humanity, this paints a possible future path. Our distant descendants, having mastered travel within our solar system, might look to the halo as the next logical step. We would not migrate to another star, but to the spaces between them. We could become a halo civilization, building enormous, self-sustaining world ships or orbital clusters, drawing energy from captured stars and the enigmatic dark matter field. Our home would no longer be a planet, but a chosen point in the great dark, a quiet neighborhood with a view of the entire spinning galaxy below. It is a migration not just of location, but of being, leaving the planetary cradle forever for the infinite freedom of the interstellar void. If other civilizations have already taken this path, then the galaxy's most advanced life isn't on the planets we dream of finding. It is all around us, hidden in the darkness between the stars, having completed its great migration to the ultimate cosmic suburb. This silence we perceive may be the sound of a galaxy already inhabited, but by beings whose existence is defined by movement. To understand how a truly advanced civilization might migrate, we turn to a powerful thought experiment known as the Kardashev scale. It classifies civilizations not by their politics or art, but by a single measurable trait: energy consumption. A Type 1 civilization harnesses all the energy available on its home planet. A Type 2 civilization commands the total output of its star, likely by building something like a Dyson sphere. A Type 3 civilization has achieved mastery over its entire galaxy, utilizing the energy of billions of stars. This scale provides a stunning framework for imagining the scope of cosmic migration. A Type 2 civilization, having enveloped its sun, would face a fundamental choice. Its star has a finite lifespan. To ensure survival, it must plan an exodus. This migration would begin within its own stellar neighborhood. Imagine a civilization that has transformed its solar system into a vast, interconnected machine. They might construct colossal world ships, each a self-contained ecosystem larger than planets, and slowly propel them toward a younger, more stable star over centuries or millennia. Their journey would be a purposeful, system-wide relocation, moving their entire societal infrastructure from a dying hearth to a new one. But it is at the Type 3 level that migration becomes the civilization's defining characteristic. A species that has harnessed the galaxy's energy is no longer tied to any single star or even any 1,000 stars. Its perspective is galactic. Its imperative is expansion, stability, and perhaps curiosity. Such a civilization would almost certainly be migratory by nature, spreading its presence across star systems not out of need, but as an inherent mode of existence. The methods of this galactic migration stretch our imagination. The most conceivable is the generation ship, a mobile world that travels for centuries between stars, with generations of inhabitants living and dying during the voyage. But for a Type 3 civilization, this might seem primitive. They might instead construct a network of stable wormholes, bending space-time to create instantaneous transit corridors between stars, turning the galaxy into a connected subway system. Or they may have long since abandoned biological form, uploading their collective consciousness into resilient, self-repairing probes. These probes could travel at near light speeds, needing no life support, and upon reaching a new star system, use local matter to build receivers and download the consciousness of others, making travel as simple as sending a signal. The impact of such a migratory civilization on the galaxy would be profound, yet possibly invisible to us. They would not build planet-bound cities we could spot with telescopes. Instead, they might optimize stars for energy harvesting, creating subtle, regular dimming patterns as Dyson swarms orbit them. Their largest structures might be in the calm, resource-rich galactic halo, where they could compute and exist for eons undisturbed. Their migration would reshape the galaxy's ecology not by conquest but by quiet, total utilization. They would flow through the cosmos like water through a sponge, filling every viable niche, leaving no trace but a faint, organized signature in the infrared heat of restructured stars. If such a civilization exists, our failure to see them might not be because they are hiding. It might be because we are looking for neighbors in houses while they have become the river. Our galaxy is not a pristine, untouched island. It is an artifact built from collisions and mergers long ago. The evidence for this is etched into the very stars around us, and one of the most dramatic chapters has only recently been decoded. It is called the Gaia Sausage, and it is the ghost of a dwarf galaxy that our Milky Way devoured in its youth. This story comes to us from an extraordinary eye in the sky, the European Space Agency's Gaia spacecraft. Gaia is not taking pretty pictures of nebulae. Its mission is astrometry, the precise measurement of star positions and motions. It is constructing the most detailed three-dimensional map of our galaxy ever made, charting the positions, distances, and velocities of over 1 billion stars. When scientists began analyzing Gaia's first torrent of data, they noticed something bizarre. A large population of stars in the galactic halo, the sparse cloud of ancient stars surrounding our bright disk, were not moving randomly. They were streaming together on highly elongated radial orbits, plunging like daredevils toward the galactic center, and then swinging far out into the halo again. When plotted on a chart, the shape of their velocity distribution was not a sphere, but a distinct sausage or meatball. Hence the playful but accurate name, the Gaia Sausage. These stars were not native to the Milky Way. They were invaders, or more accurately, assimilated migrants. The forensic reconstruction tells a violent tale from about 10 billion years ago. A sizable dwarf galaxy, perhaps 1/4 the mass of the Milky Way at the time, ventured too close. Our galaxy's immense gravity did not just pull it in gently. It shredded it. The dwarf galaxy was torn apart in a series of close passes, its stars violently stripped away and flung onto these crazy, plunging orbits that have persisted for eons. The stars of the sausage now form a significant portion of our galaxy's inner halo, a fossilized imprint of that ancient feast. This was not a minor event. It was a defining merger that helped shape the Milky Way we live in today. The collision likely puffed up and thickened the young Milky Way's disk, and may have even contributed to the formation of our galaxy's central bulge. Those migrant stars born in a different, smaller galaxy are now forever part of our home. They are celestial immigrants whose journey ended billions of years ago, but whose presence tells us our galaxy has always been a product of migration. This changes our perspective profoundly. We look up at a seemingly unified Milky Way, but we are gazing at a mosaic. Some of those faint, ancient halo stars are not original citizens. They are survivors from a galactic shipwreck, their very motion a memory of a cataclysm that helped build our cosmic neighborhood. If such a monumental merger is written in the stars, what other, subtler migrations might be hidden in the data, waiting for a map precise enough to reveal them? The Gaia Sausage is a fossil of a migration long completed. But if you look toward the southern hemisphere's sky on a dark night, you can witness a galactic migration happening in real time. Two fuzzy patches of light, the Large and Small Magellanic Clouds, sail in tandem. These are not clouds at all, but dwarf galaxies, satellite companions to our Milky Way. They are caught in a gravitational dance that is slowly unraveling them, and the evidence of this cosmic dismantling is written across a quarter of the sky in a structure we cannot see with our eyes. It is called the Magellanic Stream. This is not a stream of stars, but a vast, meandering river of cold hydrogen gas, stretching for hundreds of thousands of light years. It is the longest and most distinct trail of its kind in our galactic neighborhood, a luminous scar left by the Milky Way's immense gravity. As the Magellanic Clouds orbit our galaxy, the tidal forces, the difference in gravity's pull between the near side and far side of each dwarf galaxy are literally pulling them apart. Gas, being far less bound than stars, is the first to be stripped away. It is drawn out into long, faint filaments that trace the path of their orbit, like cosmic breadcrumbs marking their journey. This stream is a direct pipeline of raw material, a slow-motion transfer of matter from the satellites to the dominant galaxy. Over the next few 100 million years, this enormous reservoir of hydrogen will continue to fall toward the Milky Way's disk. When it finally reaches the crowded, dense regions of our galaxy's spiral arms, it will collapse under its own gravity. This is the essential ingredient for star birth. The gas will ignite, forming brilliant new stellar nurseries and lighting up the galactic disk with a fresh generation of stars. We are watching a galactic feeding event unfold. The Magellanic Clouds are not being consumed whole like the Gaia Sausage progenitor was. They are being milked, their lifeblood of gas steadily drained to fuel the ongoing growth and rejuvenation of our larger galaxy. It is a migration of potential, of pure, unformed matter, on a scale that dwarfs any human concept of resource transfer. This process answers a fundamental question about spiral galaxies like our own. How do they keep forming new stars for billions of years? Their original gas reservoirs should have been used up long ago. The Magellanic Stream provides one clear answer: they steal it. They are cosmic gardeners, drawing sustenance from smaller neighbors to maintain their own brilliant, starry foliage. This live action capture shows us that migration is not just about the movement of finished objects like stars or planets. It is also about the flow of the fundamental building blocks themselves. The Milky Way is not a static island universe. It is a dynamic, ever-changing ecosystem, actively reshaping its surroundings and incorporating fresh material from the cosmic winds. The silent, invisible river of hydrogen flowing from the Magellanic Clouds is a reminder that the Great Migration continues all around us, setting the stage for futures we can only begin to envision. The Magellanic Stream shows a galaxy pulling in resources to thrive, but this movement has a darker, more compelling counterpart. Galaxies are not just drawn toward great attractors, they are also fleeing profound emptiness. Between the great glowing filaments of the cosmic web lie the voids. These are the true deserts of the universe, regions of space hundreds of millions of light years across that contain almost nothing. No bright galaxies, no bustling clusters, just a thin mist of dark matter and the occasional lonely dwarf galaxy. If the cosmic web is a map of continents and rivers, the voids are the open oceans, vast and desolate. For a galaxy unfortunate enough to find itself on the edge of one of these voids, a powerful imperative takes hold. Astronomers call it void drift. The gravitational pull from the sparse emptiness is negligible, while the collective tug from the dense, glittering filament next door is immense. This imbalance creates a slow but relentless migration away from the void and toward the crowded cosmic highway. It is a gravitational repulsion from nothingness. A galaxy experiencing void drift is like a town built on the edge of a spreading desert. As the sands encroach, the inhabitants are forced to pack up and move toward the fertile river valley, joining the larger community. In the cosmic sense, this migration is a necessity for survival and growth. A galaxy trapped deep within a void would be starved of interactions. It would have no neighbors to merge with, no fresh streams of gas to siphon, no gravitational nudges to trigger new rounds of star formation. It would become a cosmic hermit, aging in isolation, its star formation sputtering out as it consumes its original gas supply. Its stars would burn out over eons, leaving behind a galaxy of dim red dwarfs and stellar corpses, a quiet ghost in the dark. This presents a startling possibility for the fate of life itself. Intelligence, if it arises, might face a cosmic imperative to migrate not just for resources but for connection. A civilization born in a void galaxy, no matter how advanced, would eventually gaze out at a terrifyingly empty sky. They would realize their home is drifting into a perpetual wilderness, cut off from the dynamic interactions that fuel cosmic evolution. Their entire galactic neighborhood would be a dead end. The ultimate long-term survival strategy for such a civilization would be clear: they must leave. They would need to engineer a migration of their entire society toward the nearest filament, a journey of hundreds of millions of years to rejoin the flow of cosmic traffic. This frames the Great Migration in a new, urgent light. It is not merely a drift toward greater structure, but an escape from the void. The most advanced life in the universe may not be found in the brightest galactic cores, but in the refugees fleeing the dark, silent frontiers, desperately seeking the light and company of the crowded cosmic streets. Their journey would be the ultimate testament to a universal truth that to stagnate is to fade, and to survive, everything must keep moving. The voids teach us a sobering lesson that stagnation is a cosmic dead end. But what if the ultimate escape is not from a void but from the universe itself? This is the final, almost unimaginable horizon of the Great Migration, the idea that a civilization, or perhaps the very fabric of reality, might one day leave our cosmos for another. We are venturing into the realm of pure speculation, where physics meets philosophy. The first, most dramatic possibility involves the very objects we see as cosmic endpoints, black holes. We know a black hole's event horizon is a point of no return for matter and light. But what lies at the very center, at the singularity? Our equations of gravity break down there, and some theories suggest it might not be a point of infinite density, but a tunnel, a wormhole, connecting our universe to another region of space-time, or to a completely different universe altogether. In this view, a black hole is not a pit but a potential doorway. The catch is catastrophic. Anything passing through would be stretched into a stream of atoms by immense tidal forces, a process called spaghettification. For any physical being, it is a one-way trip into oblivion. But for information, or for a civilization that has transcended physical form, a black hole's singularity might represent the ultimate emigration terminal, a brutal but functional gateway out of this reality. A less destructive but even more staggering concept is the intentional creation of a new universe. This idea springs from the strange physics of cosmic inflation, the theory that our own universe underwent a period of unimaginably rapid expansion in its first moments. Some models suggest that under conditions of extreme energy density, a bubble of false vacuum could form and undergo its own inflationary expansion, pinching off from our space-time entirely. It would become a self-contained baby universe with its own laws of physics, forever disconnected from its parent. Theoretically, a sufficiently advanced civilization might learn to trigger such an event in a laboratory. They would not build a ship to travel to another universe. They would engineer a new one and then step inside, sealing the entrance behind them. This would be the final act of migration, not just moving to a new home, but becoming the architects of that home's very existence. The motivation could be survival, as our own universe faces a cold, entropic death in the far future, or simply the pursuit of a reality better suited to their evolved state of being. While these ideas border on science fiction, they represent the logical extreme of the migratory impulse we have traced from galaxies to rogue planets. If life and intelligence are driven to move, to explore, and to escape dead ends, then the ultimate dead end is the heat death of our own cosmos. The Great Migration, therefore, might not end with the flow into superclusters or the colonization of halos. Its final chapter could be an exodus, a deliberate departure from this entire realm of existence. It forces a profound reflection on our place in the cosmos. We are part of a story that began with the migration of matter after the Big Bang, continued with the drifting of galaxies and the spreading of life, and may, in some distant future, culminate in a conscious choice to leave the stage entirely, carrying the spark of awareness into a reality of our own making. The ultimate test for any civilization may not be intelligence but endurance. The vast, silent cosmos we observe might be telling us a story not of absence but of failure. This brings us to one of the most unsettling solutions to the Fermi paradox, the concept of the Great Filter. The idea is simple yet terrifying. Somewhere on the path from simple chemistry to a galaxy-spanning civilization, there exists a barrier, a step so improbable or so dangerous that it stops nearly everyone. We have wondered if this filter is behind us, a miraculous fluke like the origin of life itself that rarely happens, or, more ominously, if it lies ahead of us waiting to be encountered. What if that filter is not about inventing radio or mastering nuclear power? What if the Great Filter is migration itself? The leap from a planetary species to an interstellar, migratory one could be the universe's most brutal bottleneck. Consider the sheer physical challenge of leaving our solar system for good. We are not talking about probes or brief crewed missions. We are talking about permanent migration, moving a meaningful population across the light years to a new star. The distances are not just large, they are psychologically crushing. Even our nearest stellar neighbor, Proxima Centauri, is over 4 light-years away. With our current technology, a voyage there would take tens of thousands of years. This forces a civilization to confront engineering problems of an entirely new magnitude. You must build a vessel that is not just a ship, but a closed, self-sustaining world, capable of functioning flawlessly for centuries or millennia. Every system, from air recycling to food production to social governance, must operate in perfect harmony without any outside help, without any chance for resupply or rescue. A single critical failure, a plague in the closed ecosystem, a gradual decay of the vessel's structure, or a rebellion among generations born into the journey could end the entire endeavor in the cold dark. The ship becomes a tiny, fragile bubble of biology sailing through an ocean of nothing, and the ocean is always waiting for a single mistake, but the filter might be even more subtle than engineering. It could be a crisis of will, a failure of imagination on a species-wide scale. Imagine humanity 1,000 years from now, having perhaps mastered our solar system. We might have thriving cities on Mars, vast orbital habitats, and mines on the asteroids. life could be comfortable, even luxurious, within our celestial backyard. The urge to embark on a desperate, generations-long voyage into the absolute unknown might simply fade. Why risk everything on a terrifying leap when you have built a paradise at home? The cost of a true interstellar arc would be astronomical, consuming the resources of entire planets. The political and social will to undertake such a project for a reward that none of the planners will live to see might never coalesce. A civilization could become too successful, too settled, too content in its local garden, and in doing so, it chooses a long, comfortable stagnation over a perilous migration. It trades immortality for convenience, and in a universe that demands movement, that choice is a filter. This reframes our own place in the cosmic story. If the Great Filter is indeed the transition to a migratory civilization, then every challenge we face, from climate change to geopolitical strife, is a preliminary round. These are tests of our ability to manage our own world, to think in the long term, and to cooperate on a global scale. If we cannot solve problems on our single, fragile planet, we stand no chance of maintaining a society inside a metal hull for 1,000 years between the stars. Our current struggles are a rehearsal for the ultimate final exam. The silent galaxies around us may be filled with the ghosts of civilizations that, like us, looked up at the stars but could not bring themselves to make the leap. They may have succumbed to war, to environmental collapse, or simply to the comforting gravity of their home world. They remain forever planetary species. The Great Migration, then, is more than a journey. It is a rite of passage for intelligence in the cosmos. To pass through this filter is to graduate from being a creature of a world to becoming a creature of the galaxy. The question hanging over humanity is not just whether we can visit another star, but whether we have the collective courage, wisdom, and patience to truly leave home behind. Our survival as a species may ultimately depend on becoming restless. The silent stars might hold the archives of ancient travelers. To uncover whether a great migration has already swept through our galaxy, we must become cosmic archaeologists, sifting through the light of suns for clues left by civilizations that may have passed this way eons ago. This search moves beyond listening for radio signals and into the realm of technosignatures, physical evidence of technology so advanced it reshapes the cosmos itself. The most famous of these is the Dyson Swarm, a vast collection of energy-capturing platforms orbiting a star. We would not see a solid shell, but we might detect a star that flickers in strange, irregular patterns as the swarm's components pass in front of it, or one that shines normally in visible light but radiates an excess of waste heat in the infrared, like a powerful engine idling in the dark. Finding such an altered star would be a monumental discovery, but it would point to a civilization still in place, harvesting its home sun. The evidence of a migration, of a civilization that moved on, would be subtler and more profound. We might look for systems with unusual chemical footprints, a species that mastered nuclear fusion or fission on an interstellar scale, could leave behind traces of artificial isotopes in a star's atmosphere or on airless worlds, elements arranged in ratios never found in nature. It would be the cosmic equivalent of finding refined plutonium in a prehistoric cave, a clear sign that someone was here, processing materials long before we arrived on the scene. Even more tantalizing would be the arrangement of artifacts themselves. Imagine a constellation not of stars but of objects, a perfect geometric formation of mirrors, satellites, or probes placed in stable orbits around a star, not for any purpose we can discern, but perhaps as a monument, a navigational beacon, or simply the abandoned infrastructure of a project completed millennia ago. Such precise, unnatural alignment would stand out against the chaotic beauty of natural orbits like a paved road cutting through a wilderness. But the ultimate evidence of a migratory Type 3 civilization would be written across the galaxy itself. We look for engineering on a stellar scale. Could a civilization move stars? The idea seems like pure fantasy, yet the physics allows for it in principle. A sufficiently advanced society might use focused light from billions of mirrors or the gravity of a carefully guided black hole to nudge stars over astronomical timescales. They might rearrange their galactic neighborhood, creating patterns, clusters, or even clear pathways through the dust and gas. They could build vast, dark structures for computation or habitation in the calm of the galactic halo, structures so large they cause microlensing events as they pass in front of distant stars, bending their light in predictable, repeating ways. Finding a cluster of stars moving in a geometrically perfect formation against the galactic flow, or a region of space suspiciously cleared of interstellar debris, could be the signature of a gardener who finished their work and left. This is the grandest puzzle of astroarchaeology. We are not just looking for neighbors, we are searching for the ghosts of architects, for the faint, fossilized imprint of an intelligence that treated galaxies as raw material. Their greatest monuments would not be pyramids on a planet, but the subtle, rearranged motions of suns, a fingerprint pressed into the fabric of the galaxy itself. If such evidence exists, it would tell us the Great Migration is not just a future possibility, but a past reality, and that we are walking through a forest that was deliberately planted by hands we will never see. Our search for cosmic architects raises a profound question about our own future actions. If humanity ever graduates to become a migratory civilization, what moral code will we carry into the stars? The technical challenges of interstellar travel might one day be solved, but the ethical dilemmas could define our legacy. Imagine our first crewed mission arriving at a planet orbiting another star, a world with its own delicate, alien biosphere. Do we have the right to land, to build, to take what we need? This is not science fiction. It is a necessary conversation about the ethics of cosmic migration. On one side of this debate lies a perspective that echoes an old terrestrial idea, cosmic manifest destiny. This view holds that intelligence confers a natural right and even a duty to expand, to use available resources, and to spread life into the barren corners of the galaxy. Proponents might argue that a lifeless, rocky world is a wasted opportunity, a blank canvas. If we can transform it through terraforming into a habitable oasis brimming with Earth-like life, we are performing a creative act, adding value and beauty to the universe. From this standpoint, our migration is not just survival, it is a noble purpose, the universe becoming conscious of itself and actively cultivating its own garden. Uninhabited star systems, rich in metals and energy, are seen as natural resources for the grand project of cosmic civilization, there for the taking by those with the capability to use them. Yet, this view collides with a powerful counter-argument, a cosmic prime directive of non-interference. This ethical stance asks us to consider the inherent value of things as they are, even in their silence. A planet with a nascent, alien biosphere, even if it is just microbial mats in a subsurface ocean, represents a unique story billions of years in the making. To introduce Earth bacteria or to radically alter its atmosphere and climate would be an act of irreversible biological contamination, a form of galactic genocide that extinguishes that unique story forever. We would be colonists, not discoverers, overwriting a native history with our own. The Prime Directive argues for extreme caution, for observation from orbit, for treating alien ecosystems as protected wilderness areas of universal significance. It suggests that a truly advanced civilization is measured not by its power to reshape worlds, but by its restraint and respect for other forms of existence. The tension between these views frames migration as our greatest moral test. Is our role to be gardeners, actively tending the cosmic plot, or are we meant to be quiet observers in a museum of natural wonders? The answer may lie in a middle path, one that recognizes both our needs and our responsibilities. Using resources from clearly lifeless systems like asteroids and comets might be ethically permissible, a way to sustain our journey without harming another's home. But the moment we detect even the faintest whisper of biology, the rules change. That world becomes off-limits for settlement, a sanctuary to be studied with reverence from a distance. Our migration would then become a careful navigation, not a conquest. We would thread our way between the stars, taking only from the dead to sustain the living and leaving the living utterly untouched. This ethical framework turns the Great Migration into a pilgrimage of respect. It means we might traverse the galaxy, not to claim it, but to witness its wonders and ensure they endure long after we have passed through. Our legacy would not be one of conquered worlds, but of worlds preserved in their pristine, alien glory because we chose to look and not to touch. The ethical frameworks we craft for the stars will only matter if we find a way to get there. Our future as a migratory species hinges on confronting the immense, cold reality of interstellar space. The distances are not merely large, they are psychologically absolute. Our nearest stellar neighbor, Proxima Centauri, is over 4 light-years away. With our current propulsion ideas like nuclear fusion rockets, that journey could still take centuries. This is the fundamental barrier, and it forces us to consider pathways that sound like science fiction, but may be our only options. The first and most tangible is the generation ship. This would be less a vessel and more a mobile world, a self-contained ecosystem housing thousands of people. It would be a city sealed in a bottle, hurled into the dark. The engineering challenges are beyond monumental. You must create a closed-loop system that recycles every drop of water, every molecule of air, and every nutrient perfectly for hundreds of years. The social structure would have to be incredibly stable, designed to maintain purpose and cooperation across generations born into the metal halls who know nothing but the journey. A single failure, a plague in the hydroponic gardens, or a fracture in the hull would mean extinction in the void. The generation ship is a gamble of staggering proportions, betting that human society can remain sane and functional in a tiny, isolated world for longer than our recorded history. This leads to the dream of bypassing time altogether through hibernation or cryosleep. The idea is seducing: to put the crew into a state of suspended animation, letting machines tend the ship while they sleep across the centuries. But the biological hurdles are immense. We are not bears. Safely freezing and reviving a complex human body, with its trillions of cells and delicate brain structures, is a problem we have not begun to solve. Even if we could perfectly preserve the body, the ship itself remains vulnerable. Who repairs the micrometeoroid damage after 200 years? Who reboots the failing computer? Cryosleep may reduce resource consumption, but it does not eliminate the need for a resilient, automated ship and perhaps an awakened caretaker crew cycling in and out of sleep, a concept filled with its own profound loneliness. A more radical pathway abandons the body entirely, mind uploading. If consciousness could be translated into data, the journey changes completely. The ship becomes a sophisticated computer server, powered by a small reactor carrying billions of digitized minds. Travel time becomes irrelevant to the passengers, who could experience a simulated universe or simply have their processes paused for the duration. Upon arrival, advanced nanotechnology, also carried aboard, could use local resources to build synthetic bodies or robotic forms to house these consciousnesses. This solves the problems of life support, aging, and even societal strife. But it raises existential questions that dwarf the engineering ones. Is the uploaded copy truly you, or just a perfect replica? Would we be migrating as humanity or as its ghost? Our choice of destination defines the mission. Proxima Centauri beckons simply because it is the closest, with a rocky planet, Proxima b, in its habitable zone, though it is likely battered by intense stellar flares. The TRAPPIST-1 system, about 40 light-years away, is a more tantalizing target with 7 Earth-sized worlds, 3 of which orbit in the temperate zone. It is a compact solar system offering options, but it orbits a volatile red dwarf star. Perhaps the most mysterious destinations are the rogue planets, the dark nomads flung from their stars. A large rogue with a subsurface ocean heated by internal geology could be a haven, a hidden oasis in the perpetual night. Reaching one would require incredible navigational precision, as they emit no light to guide us, but it would offer a world completely independent of a star's lifespan. Embracing any of these pathways is not merely an adventure, it is an evolutionary imperative. History shows that species which do not expand, which remain confined to a single ecological niche, are vulnerable to extinction. A single planet, no matter how well managed, sits under a multitude of cosmic guns, from asteroid impacts to nearby supernova to its own star's eventual death. To place all of humanity's eggs in one planetary basket is, on a long enough timeline, a guarantee of oblivion. Becoming migratory is the ultimate act of insurance. It transforms us from passive residents of a solar system into active participants in the great cosmic story. We would no longer just be observing the flow of galaxies and the drift of stars. We would be joining that flow, adding our own tiny, deliberate current to the grand migration of matter and life across the universe. Our survival may depend on learning to become comfortable with the endless journey. The universe is not a random scattering of lights. It is a meticulously organized network, a three-dimensional spiderweb of unfathomable scale. This is the cosmic web, and it is the ultimate map for the Great Migration. Picture the filaments of this web as cosmic superhighways, vast rivers of dark matter and gas stretching for hundreds of millions of light years. Galaxies are not scattered randomly across this network. They cling to these luminous strands like beads on a string, and they move along them. This is the gravitational infrastructure that guides everything. Our Milky Way, along with the entire local group, is traveling along one such filament right now, flowing toward the dense knot of the Virgo supercluster, which itself is moving along a larger strand toward the immense Shapley supercluster. These filaments are not just passive roads, they are flowing with the galaxies. They are the channels that direct the grand, hierarchical drift of matter from the voids toward the dense nodes. For any civilization dreaming of interstellar travel, this map is not just interesting, it is essential. An advanced species would not plot random courses between stars. They would follow the gravitational geography, using the natural flows of the cosmic web for efficient, long-distance travel, moving along a filament where stars and resources are relatively closer together. Would be like using an interstate highway instead of navigating a trackless desert. It provides a structured pathway through the immensity, connecting vibrant galactic cities and resource-rich regions. This single image ties every thread of our story together. The rogue planets are the solitary hitchhikers on these dark roads. The hypervelocity stars are the speedsters blasted onto lonely exit ramps. The merging galaxies are the bustling interchanges where traffic converges. And the silent, migrating civilizations we have imagined, they would be the ultimate navigators, reading this ancient gravitational map to plan their eons-long journeys. From the largest superclusters to the smallest microbial spore drifting on a comet, every migrant is part of this connected, flowing system. The cosmic web reveals a universe that is not static and separate, but dynamic and intertwined. We are all riding the same currents, passengers on a journey whose final destination is written in the geometry of space itself. The map of the cosmic web is drawn, but its deepest legends remain untranslated. For all we have traced the flows and destinations, the fundamental forces steering this grand migration are still cloaked in shadow. Our journey is propelled by gravity, the great attractor that pulls galaxies together. Yet a more mysterious force works in opposition, a phantom pressure known as dark energy. We can measure its effect, an acceleration in the expansion of the universe itself, but we do not know what it is. This creates a profound tension for the future of cosmic migration. Will the gravitational pull within the cosmic web remain strong enough to keep galaxies flowing together, merging and migrating along their filaments? Or will dark energies push ultimately become dominant, stretching the cosmic web so thin that the threads snap? In that distant future, the great rivers of galaxies could slow to a halt, then reverse as the space between all structures expands faster than gravity can pull them together. The universe would become a place of profound isolation, where every island galaxy is carried away from every other, and the great migration of matter grinds to a silent, eternal stop. This unknown fate hangs over everything. Are we witnessing a temporary phase of cosmic gathering before a final, irreversible dispersal? The answer lies in the nature of a force we cannot see or touch, a reminder that the story's ending is not yet written. And what of the strange current that seems to pull on the edges of our observable universe? The phenomenon of dark flow suggests our entire cosmic neighborhood, perhaps our entire visible universe, is in motion towards something immense beyond the horizon. This is perhaps the ultimate unanswered question. Is there a structure so colossal, so unimaginably vast that its gravity tugs on everything we can see? It could be a concentration of mass and galaxies on a scale that dwarfs even the Shapley supercluster, a true cosmic continent lying in the unobservable beyond. Or, more mind-bending still, could it be the gravitational influence of another universe entirely, a neighbor in a multiverse brushing against our own? Dark flow hints that our map is incomplete, that the cosmic web we study is merely a local neighborhood within a far grander geography we may never access. The migration we are part of might be a sub-journey within an epic voyage we cannot comprehend. These mysteries of force and scale lead to a more intimate, haunting unknown. As we look out at the silent, drifting stars, we must ask, are we the only ones contemplating this journey? Is the galaxy a quiet sea, with Earth preparing to launch its first fragile raft? Or are we oblivious to a bustling network of migratory paths already in use? Our searchers for radio signals or Dyson swarms might be looking for the wrong things. A truly advanced migratory civilization would not be anchored to a star broadcasting its presence. It would be in transit, its technology so efficient and integrated with the environment as to be invisible. Their pathways might use gravitational assists around dark matter clumps or follow lanes of calm space between stellar nurseries, routes invisible to our crude sensors. The probes they send might be the size of dust grains, self-replicating and silent. The galaxy could be alive with traffic, a cosmic interstate humming with journeys, and we are like ants beside a highway, unaware of the purpose, direction, or even the existence of the vehicles rushing past. Our primitive senses and short lifespans might blind us to a reality of constant, majestic motion. These unanswered questions are not failures of science. They are the engines of discovery. They are what drive us to build better telescopes, to launch deeper probes, to run more complex simulations. The mystery of dark energy pushes us to understand the fundamental fabric of reality. The enigma of dark flow compels us to consider the shape of all existence. The silence in the heavens challenges us to expand our imagination about what life and intelligence could become. This pursuit, this relentless need to understand our place in the flow, is itself a form of migration. We are migrating in mind, charting the unknown territories of knowledge, driven by the same restless impulse that may one day push us to migrate in body. The great cosmic migration is not just a story about where things are going. It is a story about why we look up and why we feel deep in our bones that to stay in one place is to miss the point of the universe entirely. The night sky is a map of journeys, not a fixed portrait. From the immense, slow drift of our galaxy toward unseen superclusters, to the lonely exile of rogue planets sailing the dark, the universe is defined by motion. We have traced stellar runaways flung from black holes, witnessed galaxies consuming each other in slow motion mergers, and pondered whether life itself might be a stowaway on comets or a deliberate seed sent across the light years. The cosmos is not a museum of still exhibits. It is a living, flowing system, a grand narrative written in trajectories and velocities. Even the silence we perceive may be the sound of intelligence that has already moved on, having migrated from planetary cradles to become creatures of the galactic halo or beyond. This relentless motion suggests something profound about existence itself. Perhaps the urge to explore, to journey, to migrate from one point to another is not merely a human impulse. It could be a fundamental principle woven into the fabric of reality, from the smallest quantum particles to the largest clusters of galaxies. Everything is restless. Everything is seeking a new equilibrium, a different vantage point, a next chapter. So the next time you stand under the stars, try to see them differently. See them as waypoints, see them as past homes or future harbors in an epic voyage that encompasses all of space and time. You are not looking at a static ceiling. You are gazing at the open road of the great cosmic migration, and we are all, in some way, already